Okay, everybody, I hope you all had a good break. I just want to, I feel like we've been gone a long time. I feel like I've been gone a long time. I was in Boston for almost 2 weeks, and I just got back last night. So this is as much for you guys as for me, because I want to just remember where we're at. So let me just go over this. Okay, so what we're doing, we have an exam coming up on Wednesday, a week from Wednesday. That's exam 2. And so we're going to finish, hopefully, everything that's going to be on the exam this week. We might have to do a little bit in chapter 38 on Tuesday. If we have to do too much, I just won't include chapter 38. We'll just see how far we get. But right now, the plan is that we're going to go through chapter 38 and hopefully get most of it done before Tuesday. I don't want to give you new material before the exam on Wednesday night. So you had this. So what we're going to do, let me just show you the exam schedule. You have all the room locations, same as last time. And if you want to sign up for the online exam in Proctor U, if you have conflicts and you want to do that, that's going to be posted really soon. It's not available yet. I'll do that today. So also, you're probably wondering, now that I'm talking about exams, the study guide, and I'll get that up before next class. So the study guide for exam 2. So that's where we're at. And the other thing I want to draw everyone's attention to is this R bonus assignment 1 was due, you might know, before the Friday, 2 weeks ago. But a few people wanted extra time. Remember, I said I could do that because we didn't have office hours. I wasn't there for a few of those days. So I extended it. So it's still up there if anyone chooses to do it, if you're interested. Now, you're not going to be tested on it. You don't have homework assignments on it. This is just, and it's just for bonus. So don't feel obligated to do it. Okay? And now this exam 2 conflict, that's the same, that's at 4:30 the same day, and that is not posted yet either. That will be posted later today. So any questions about this calendar, about anything? Okay. So let's go to the document camera and remember where we left off. So, okay, so we are starting chapter 34, but just let's recall on the previous page, in chapter 33, we just started multiple regression with quantitative predictors. And we said, okay, now that, with just one X, homework predicting final, for example, you have a plane. But when we add another one, we add another dimension. So now we're in 3D, which we're still able to visualize. And here's a 3D picture of, here's the multiple regression equation. And this is, it looks like, this is, you can see that this slope for exams is greater because exams seem to have more of an effect in predicting final, they're a better predictor of final. And the homework is still a predictor, but it has less of an effect. Okay? Now what we're going to look at today is how these two slopes, you'd probably think that these two slopes are the same as when you predict homework predicting final or when you predicted exam, but they're not. They've changed. And that's what we're going to look at, why and how we get the slopes in multiple regressions. So that's what we're going to, and how we visualize them and how we think of it. So it comes up all the time because you often want to have more than one variable predicting a y. Okay, so the first thing to note is that these slopes in the multiple regression are not the same as in the simple regressions. Now let's recall the simple regression. So here's a simple regression where we have homework predicting final. We're just in a plane. You're very familiar with this and you know how to get the slope. And here's our correlation. So this is our slope for, if we just have a simple regression, okay? And here's the one, we did the same thing with exams. We get a bigger slope than this one, has a stronger impact. It's 0.66 versus 0.34, right? So these, you'd think that when you put these two together, you'd think, well, why did the slopes change? But look, when we put them both in the multiple regression, right at the bottom of the page, look what happens. This one, 0.34, went down to 0.16. And the other one went down too, from 0.66 to 0.58. So they're not the same. All right. So the only time they are the same is when we're going to look at this later, but just they can be the same, but only when the homework and the exams have nothing to completely independent. They're not correlated. When they're not correlated at all, then if you put them in the model, they wouldn't change. But usually your predictor variables are somewhat correlated, and certainly people who do better on the homework generally do better on the exams too, so they're correlated. All right, so now let's look at what we have here. So do you remember that we have this multiple correlation coefficient, capital R? And remember that the correlation is just defined between two sets of numbers. You know, you take their z-scores, you standardize them, get this common measuring stick, change them into z-scores, and then you multiply them together. Do you remember how you compute that correlation coefficient? Well, if you have three sets of scores, it doesn't work. It wouldn't. You could have a positive, a negative, it just wouldn't make sense. So you need two sets of scores. So what the correlation, we talked about this before, but you might forget. The correlation is between two sets of numbers. It's what you predict finals to be, what you predict them to be, and what they actually are. And the stronger they're correlated, the stronger your R is, right? If you could make a perfect prediction, and the prediction based on the homework and exams and this multiple regression, if you make this prediction and it comes out, you perfectly predict it, well then you'd get a correlation, you'd get the final scores that you predicted would be exactly the same as students' actual scores, right? So you wouldn't have to take the final. I could say, oh, from your homework and your exams, I can perfectly predict your final score. So you wouldn't even have to take it. So, so that's what this R is, all right? Do you remember that? That's what that is. Okay, but then there's also these three simple R's that aren't the same. They're not the same. This is the R between the final and the homework. Like here's a correlation of 0.39 between the homework and the final. And here's a bigger correlation of 0.5953 between the exams and the final. And then there's another one. What do you think? The other one, so I'll write this down. So this is like R between Y, the final's Y. So it's between Y and X1. And here's an R between Y and X2. And now here's another R that's between the two X's. That's what this one is, between X1 and X2. And if that's 0, if it's uncorrelated, then these slopes will be exactly the same. You don't have to worry about it. But if there's any correlation there, they're going to change. That's the idea. Okay? So now you might wonder why we would want to put these two together. Why would you want to put multiple variables? What do we gain? We see that both plots show a linear trend. Why do we want to do a multiple regression? Well, we actually can make a better prediction. We can make a better, if we combine the information from more predictors, we can make a better prediction. And what we can also do is, and this you might not, this is probably very intuitive to you, but this you might not be aware of, is that we can look at the effect of each predictor while controlling for the other predictor. We can separate out the effects of how much of people's, okay, I'll read this first because it will help you understand it. All right, we get a different coefficient, a different slope when we control for the other predictor. Okay, and in some examples, multiple regression coefficients will give a better estimate of causal effects, not just predictive ones. than the simple coefficients do. And the reason we get what we're doing when we control, you see, people who have higher exams also have higher homework, so some of this effect is because of homework. And the idea is that since they're correlated, maybe I'll just draw a little picture. When, let me see how I should draw this. Okay, so when the two x's, when r between like x1 and x2 is equal to 0, the picture is kind of like you have an x1, let's just make a circle here, and an x2 with different, and they're both contributing to the final, but they don't really have any relation to each other. So, so your slopes in the multiple, if that was the case, these slopes would be the same. So when it looks like that, the slopes in the multiple regression are exactly the same as the ones in the simple. Okay, so these would be the same, and these would be the same, sorry. Okay? The slopes in the multiple regression are equal to the slopes in the simple regression. But here's the picture we have instead. When the correlation between x1 and x2 is not equal to 0, and it's not, they're correlated, quite correlated. When they're not equal to 0, then it's like one visual that helps students is like their overlap. They have some overlap. So some of the effect of homework is actually due to the effect of the exams, and some of the effect of exams is due to the homework. They have this overlapping effect right here, and so it's almost like if we count, and they're both predicting finals. So now the slopes in the multiple are going to be different, are not equal to the slopes in the simple regression. In this case, it's almost like you'd be double counting. You'd be double counting this part where they're sort of predicting the same thing. So that's the idea. So they're both smaller here. And that's always going to happen if they're all positively correlated. But if some of them are negatively correlated, it's more complicated. All right. So that's the idea. In multiple regression, we're going to let the computer software calculate the slopes for us, since we'd have to adjust for the R's and the SD that we used before to account for the additional variable, and the calculations are just very tedious. So until you know matrix algebra, until you take, like, I don't know how many of you have, you'll learn how to solve for the slopes then. But without matrix algebra, it's very hard. I'll try to do a job. I'll try to do a good job of explaining the idea to you, and you'll see. And you'll understand it. And we'll do a simple calculation. But we're going to let the computer do the calculations for us. All right. So we can answer these questions. It says, do the slopes in the multiple regression equation, do we have the same slopes? No, we just answered that. We do not have the same slopes, sorry. And why do they change? They change why? Because the correlation between x1 and x2 is not equal to 0. They change because they take into account how the homework and exam averages are correlated. That's the idea. And here's a correlation matrix. You're going to see this all the time if you do multiple regression. On every printout, this is one of the most important things you can look at, is this correlation matrix. So let's take a look at what it does. So it gives you, so here you have your y, and you have x1 and x2, and you have the same y here, and x1 and x2. And notice how this diagonal here is 1. Do you know why? We can write y. We can say the diagonal is equal to 1. Can you tell why? Can you see why? Because what's it saying? It's saying how homework is correlated with homework, how x1 is correlated with x1. This right here, all of these right here, are just saying how a variable is correlated with itself. And of course, there's a perfect correlation between finals and finals and between exams, your exam score and your exam score, right? So it's because, you know, our XX or YY or XY is equal to 1. Okay? But do you also notice how it's also symmetrical? Like this, for example, is the same as that. And this one, and that's always going to be true, is the same as that one. Do you see how these are all the same, these diagonal ones. And the off-diagonal ones, excuse me, that's the off-diagonal, are symmetrical. Why? Can you tell why that would be? If I'm going too slow, tell me. It's because I'm just coming back from break, so I'm going really slow in my mind. So just tell me to speed it up if it's too slow for you. Too slow for anyone? Raise your hands. Okay, good. So the off-diagonal are symmetrical, and why do you think that would be? Let's just check it out and look at it. So what is that saying? That's saying the correlation between x1 and x2, between homework and exams, is the same as the correlation between x2 and x1, exams and homework. And that's true. That's completely symmetrical. You know, if you can, it's the same correlation. Do you understand that? It's exactly the same. It's not the same slope, but it's the same R between the two of them. Because think how R is computed. It's just the product of the z-scores. And that's commutative. Zx times zy is the same as zy times zx. So that you got. Okay, so let's write that down. So now you understand this correlation matrix. All right. So the only time those slopes wouldn't change would be of what? The ones between, where do we have it? Between x1 and x2, this one right here, between the two x's, if that was 0. And you're not going to see that very often. So we have 3 correlations we have to take into account in the multiple regression equations. And this is the new one here, between the two x's. Okay? This is x1 and x2. This is that. All right. Now, what are we going to be doing here? All right, so now this is my attempt to explain. I told you you're not going to have to put together, come up with these slopes here. By the way, you did put together stratified slopes. That's different. That's different than you had. We just stratified there. This is like 2 separate things. I don't want to confuse you. I probably shouldn't have even said anything. Okay, so let's focus on why the homework slope decreased. Why did it go down? Let's try to figure out why it went down from this to this. You know what? I think it's better if we just do it. I'm going to just do the arithmetic. So I'm just going to do it for you, even though we're not going to generally do this. Okay? You'll have one homework problem, maybe an exam problem, but in general, I'm going to work backwards, which is very much easier to do. I'm not going to ever ask you don't have to go in this direction. I'm going to be working backwards. We can see how it works by working backwards from the full model, and I think you'll understand. I think that's the easiest thing to do here. So we start with this full model, right? Right here. And how do we get that? Why is that smaller? I mean, why is this one bigger? So what we have to do to get the simple model, what do we want to do? To go from here to here, we want to eliminate exams, right? So we want to substitute in for exams. We want to write exams. We want to put this right here for exams. Do you see if we did that? And what is this? This is that relation. This is the simple regression equation between homework and exams. It comes from here, between homework and exams. So when we have this right here, what we can do is just substitute that in for the exams, and then you'll get an expression right here. Do you see how you'll get that? You just put this in for exams, and then you get that, and you can multiply those two together and add it to that, and you get right here this. You see, here's your simple one. That's what you started. That's the separated partial slope right there. And this right here is the part that the exams, the part of the exams that were really due to the homework. So you add those two together and you get that. Okay? Does that make sense? Should we do an example together? Maybe helping. I don't know if maybe reading this first would help you understand it. You see this homework slope right here in the multiple is saying what? It's saying for each extra point that students score on their homework, they score an additional 0.164 on their final. But that's after taking out the effect of the exams. So for people who have the same exact exam score, this is how much their homework's going to contribute. So after we already, think of it this way, after you predict finals from exams, which makes a really good prediction, this is the extra part that homework contributes. It's actually called a partial slope. These are partial slopes. They're the part of the slope once you separate out the effects of exams and homework, if they're correlated. So for example, for everyone who scored an 80 on the exams, an extra point in the homework will increase their final score by that much. That's what that's saying. And sometimes, you can have something that's significant, like here, but then once you put exams in, put another variable in, it disappears because it was really mostly due to a different variable. That's the idea. Is there anything left that homework itself is predicting? Because people who do well in the homework do really well in the exams too. So maybe this, right, so that's why you have it's bigger. And then once you put it into here, it's just the part of the homework that helps for people who have the same exam scores. So if you look at two people who have the same exact exam scores, the one who does better on the homework will contribute this much more. Whereas here it's kind of ignoring it's mixing the two together. And that's why multiple regression is so useful, because you really get a better idea if you understand what it's doing for each, what each variable is doing, how much they're contributing. Do you understand? Does that make sense? All right. So the homework and slope in the simple here is saying that for each extra point that students score on their homework, they score more, 0.3436 on their final, on the average. But that's ignoring their exam averages. And the problem is students with high homework averages also have higher exam averages. So some of that right here comes from having higher exam scores. How much of the increase can be predicted from homework and how much can be predicted from exams? Including them both here separates out the two effects. So here's another way that we can think about it. This helps me when I was trying to figure this out, because it was confusing when I first learned this. So here's another way. After we predict finals from exams, how much more can we improve by adding in homework and vice versa? So it separates out those two effects. All right, that's the idea. Okay, so now I think you'll understand better. Once we do that now, let's think about it. So what we're going to do is we're going to take this, we're trying to figure out, like, okay, here's after the exams has been separated out. And now I'm just showing you, it's very easy to go in this direction and say, okay, we know that if we want to get back to the simple, mix them back together, if you want to go this direction, it's algebraically very easy to do. Going this direction, it's basically matrix inversion makes it super simple, but you can just solve a matrix equation, but you haven't had that yet. But this way you don't need that, and it's easy to, you'll understand it just as well. But you're not going to have to do it, not get these slopes. All right, so now let's try to understand it again. So we start with this full model, right? We start with this. And now to get the simple model, we just have homework here. So we want to eliminate the exams, all right? And just focus on the homework. So we have to get exams. We're going to substitute in that simple regression equation. Exams equals something times homework plus an intercept. Now, why am I forgetting about the intercept? Because we're not dealing with the intercept. The intercept's going to change, but we don't have to worry about that. We're just focusing on the slopes, and generally you don't really care about the intercepts. So yeah, the intercept's going to change, but we're not worrying about that. So we're just worrying about this part right here. We're saying, okay, now we have an expression for exams written in terms of homework, and we want to eliminate exams, so we can just substitute that in here, okay? And that's what I do here. I just substituted it in. And now you can see that we have a full model that has no exam in it. So now that's our simple, that's how we got that. So you can think of this as the part, we expect that one extra point of homework leads to a small 0.1641 exam extra final points, and that one extra exam leads to that. This is the one that you trust, right? But if we get back to the simple one, they're going to be mushed together, and some of this effect, and this tells you what proportion of that effect is really due to the homework. That's the part we can predict by the homework. I hope that helps. Do you want to, you can read this again, and maybe if we do an example together, or you could do it for homework. How many people want to do this one together? Raise your hand. Okay, so we'll do this again. So we'll do the same thing, okay? We have the same thing, but now what do we want to do? We want to eliminate what? Homework. We want to go back and get this simple one. So the first step, let's write it down, is what? We're going from here to here, so we need to eliminate homework. Okay? So what are we going to do? So our second, so what do we want to do? We want to eliminate homework. We want to write it in terms of exams. So I'm just going to, okay, so here I'm not going to use our betas or anything. I'm just going to say we want homework equals something times exams plus an intercept, but we don't have to worry about that. Okay, so we just want that slope, right? And do you remember how are we going to get that slope? Do you remember what the slope is? The slope is R times SDY over SDX. So R was given to us right on the previous page, wasn't it? It's this R right here between homework. See, this, we're going to get a different equation because now this is exams equals something times homework, but now we want homework equals something times exam. But this R is going to be the same, so we're just going to use that R, right? So that's 0.3. Actually, it's really good you asked me to do this because that was just given to you. We have to figure out how you get it. Okay, so that's R. Now, SDY over SDX. Which one's Y and which one's X? Well, we're predicting, whatever you're predicting is Y. So homework is Y, and that's X. So now we need these, the standard deviations of homework over something over something. Okay, so we did that where was it? When we first were looking at, this is the same example. Here it is, right here on page 158. Right? This is it. So, what is it? 11.73 over 9.197. This R is the whole multiple regression R. Okay, we'll do that then. So now we get 11.73, that was for homework, over 9.197. Okay, and that, I calculated that to be 0. Sorry for all the decimal places. Okay, and this, so that goes right here, 0.5016. And that's what's going to go in for homework, right here. We're going to put this in for homework. And then you see if we do that, we can write it now, so we'll write it again. So what do we have now? We have final equals 0.1641 times that. For homework, I'm just writing that. 0.5016 times the exams plus, this is the separate part, plus, so this is the part that's due to the homework, and this now is just due to the exams alone. Plus an intercept, and we don't have to worry about that. Intercept, it's different each time, so you really don't have to, just know it's there, but it's different and we're not worried about that. We're just trying to get the slopes. All right? So if you want to think of it, here's a way you can think of it, that here's the part of the final. When we're predicting the final, here's the part, it's pretty small. When you multiply those two together, you can think of that as kind of the overlap part, the part we were double. This is the part that's really due to the homework. It's just inside the exams, that part. And we're adding it to the part that's, to the partial slope, to the part that's solely due to the exams, not the homework. I shouldn't say due to, because I'm not sure it's predicted by. And when you add those two together, you should get that. See, people always get prediction and causation mixed up. So I'm saying it's caused by, it's really, I don't know if it's caused by, we haven't proved that. It's predicted by. Okay, and then if you add these two together, you should get 0.6647. So I just developed this as a way to help you understand it without matrix algebra, because it really gives you a feel for understanding it. You get, I think in specs, maybe, well, just as good understanding. It's just, you can't, it's a lot of algebra to go in the other direction. So that's what we do here. All right, that's pretty much it. Any questions on that? All right. And you have a homework problem I already posted that's just like this. And it walks you through the steps so you can do it. All right. This is just so you understand it. Let's move on. So now, here's a summary. It's a really good summary here, so you should read it all. We haven't talked about interaction terms. Have we talked about interaction terms yet? We've talked a lot about them, but I don't think we figured them out for... Did we? We probably did. We've talked a lot about them. Okay, but anyway, if you don't have an interaction term, and these are just the main effects, what would an interaction term be? We're going to talk about it again, so you'll see. It would be, you'll see. So multiple regression assesses the effect of each, this is super important, each predictor variable while controlling for the other. That is, keeping the other predictors constant. And then if different x's are correlated, the slopes, the coefficients, those betas are not the same. And the slopes in the multiple regression, this is a useful term because it helps you understand it. The slopes in the multiple regression equation are called partial slopes since they quantify the effect of each x variable on the response y after the other x variables are partialed out or controlled for. That's another word for control. You partial them out. So we're going to look a lot at this. We're going to look at this next. So multiple regression with no interaction term forces all the variables in the model to have the same slopes for all the levels. Okay, and under some circumstances, multiple regression can be used to separate the causal effect of one x from another on y, from the confounding effects of other x's. And this is super important. We're going to see this. You'll see this. I said, okay, so if they're always, the x's are often correlated, but if they're highly correlated, you have to be very strange things can happen in your, when you look at the multiple regression. So beware of multicollinearity. You'll see that term a whole lot. Highly correlated x variables. What it means is that if two predictor variables are highly correlated, do not put them both in the model, because do not put them both in the model. And this is an example that helped me think about it. Is, for example, your right foot size is a very good predictor of your height, and so is your left foot size. It's extremely high correlation, right? But they're very highly correlated with each other. And if you put them both in the regression model, if you put both the right and the left in, either one or both of them could end up being not significant at all, which isn't true. It's just that they're both predicting the same thing. So if you put them both in the model, it's almost like any linear combination of the two of them. Any combination, any slopes of any of the two of them is going to be a good predictor. And sometimes it just picks one depending on the little bit of random noise in your model. It will change. With different sets, you'll get one be eliminated, then the other. It's very dependent on your particular data set, even though both of them alone are excellent predictors. And you understand why. You don't need them both. Think about it this way. Once you have your right foot in the model, how helpful is it to add the left foot? Right? And sometimes it will say, oh, the left foot's important, not the right foot. It will just be crazy. We understand this. For this, it's very important to keep these types of examples in your head, because often you don't think of that. There's an obvious example, and it happens all the time. So look at that correlation matrix, and if they're super highly correlated, don't trust. We'll look at it. We can look at some examples of that later. Okay? So let's move on. Any questions so far? Okay. Now, we're just going to look at these slopes graphically, and I think will help you. So we're just looking at this. We have the same multiple regression, and we're moving on. We're just looking at what things are doing here. So let's just write it down. So what are we doing? We're predicting these final exam scores by what? We have this model that says 16.4. I'm using real data here, and it's too many decimals, but plus 0.5824 times the exams. The reason I'm including all the decimals is because we're going to look at it in the data program, and I want you're all going to get randomized versions. It's useful to keep them all in because you're going to be looking at data programs a lot. Okay, plus, okay, so we usually write it with this intercept first. I didn't here, sorry. And then, okay, so the intercept often comes first. Okay, we just wrote it this way. Now, so let's look at it visually, all right? So here's the same thing. Here's our multiple regression equation. And the slope for each predictor variable controls for the other variables. So I just want to give you a visual of what that's doing. So, so let's look at it. This is just repeating what I said before. The homework slope in the multiple regression describes the effect of homework on finals for those with the same exam scores. So for those with the same exam scores, the predicted final is 0.1641 higher than, for each 1 point increase in homework, right? So this is what it looks like. The multiple regression equation estimates final scores separately for each exam score. But it's not necessarily true. It's going to give the same slope. So let's do this example. Find the 3 multiple regression equations for those who have exam scores, what? 90, So exams equal to 90. See how they're all parallel slopes? That's what it's going to give you. Exams equal to 80 and exams equal to 70. Okay, so it's going to give you the same slope. What part's going to be the same? Well, this part right here. See? So you're going to get the same slope for all of them. So so what's this equal to? You're just going to plug in 90 for exams. I'm not going to do it for all of them, but you just say plus 0.5824 times 90, right? Plus 11.91. And that's what you're going to do for each one of them. So what do you get? This is plus, this ends up being together 64.326. And you'll do the same thing here. You can see what would happen. It's pretty, when you just, the only thing you're changing is that 90 to an 80. So that's going to go down by what? That's going to go down by 10 times that, 5.824. So if you put an 80, you just put an 80, it's pretty easy. And then it's 50, this would end up 58.502. And this will end up 52.678. It's just arithmetic. I just want to show they're all parallel. Why? Because they all have the same slope. It doesn't change. If we put an interaction term, it would change. You'd have a term that was homework times exams. So for the different exams, you're going to get different slopes. So what's this saying? It's saying that, that homework has the same effect no matter what your exam score is. That might not necessarily be true. Homework might have more of an effect on people who have low exams, for example, than high exams. But multiple regression forces them all, unless you put those interaction terms in. All right, so then so that's what this looks like. So this is the multiple. Now what is, we'll look at it in a plane in a minute, but this is in a plane. But what does simple regression do? So this is simple, the same thing, simple regression. So now, what is this doing? Simple regression, if you just look at homework, the simple regression estimate final scores from homework ignoring exam scores. So you can't tell how much the exam scores account for the increased finals and how much the homeworks do. So if you include the exams, it sort of has the effect of breaking into subgroups and stratifying. See how it does that? Because right here it looks like, here's the simple regression. You see why it looks like this? Because people who have the low exams also have the low homework. So it's not, it's just, so it's conflating the two. So in this case, the simple regression equation shows a stronger effect. Shows homework having a stronger effect. A stronger prediction. That it really does. Once we see it, some of it's due to the exams, because you can see why. So so this is what it looks like in the simple, and then once you basically it's like stratifying it. Now you see it doesn't have as big an effect. The slope went down, and it went down. I wish it, when everything is positively correlated, it will always go down in the multiple. But when there's negative correlations with some of them, it's hard to tell what's going to happen. Okay, so that's the idea. And now you could do the same thing, and here's how they look in the plane. Those three that we just did, where are they in the plane? Those ones that we just did are, we can place them here. What did we have? The homework is the slight slope, right? This is this slight one. And so what do we have here? This is the strong one. So we have 90 no, 100, 90, 80, 70, 60, 50. Okay, so here we go. So this is the exams. Remember, that has a steep slope. And this right here is the homework. This one's the homework slope. That's the steep one. And so now we go from 70 on the exams. So that's this one we just did, right? 80 on the exams, and 90. That's the ones we just saw. And it has that, right? 70, 80, and 90. So this is the 3 parallel lines from the previous plane. I drew them here. Okay. So I'll write that down. The 3 parallel lines from page 165. That's parallel. Okay? Now we're going to do the 3 parallel lines here. We're going to do 3 other parallel lines. Okay. So now we're going to, what are we going to do here? So the exam slope, it's going to be steeper. It's going to be these steeper lines. Describes the effect of exams on finals for those with the same what? So this slope right here, this slope, for those with the same homework, okay? For those with the same homework, the predicted final score is what? 0.5824 points higher for each 1 point. So these slopes are going to be the same. We're going to get parallel slopes. We don't have an interaction term. And let's just put them in the plane so you can get a feel for what they look like. Okay, so how are they going to change here? If we put a 70 in here, where are we going to put the 70 in? Here, right? And add 11.91, put a 70 in there, and add 11, right? Because those for 70, so I don't think I have to do it again. I got 23.397, and here you put an 80, and it's going to be how much more? 10, it will be 1.641 higher. And I got, if you add 1, you see, 25 oh, it's arithmetic. I don't want to, I think if I just went through it, it's too time consuming. I just am telling you the answers and you can do it. 26 point, it's just substituting in the 90 there and you'll get that. It keeps going up by 10 times that. All right, so now where are they on here? Well, these are the homework, and it goes from 30, 40, 50, 60, 70, 80, 90. Okay, it goes 30, 40, 50, 60, 70, 80, 90, 100. 30, 40, 60, 70. So 70 is there, right? So this is the 71. This is the 81. And this is the, did I do that wrong? This should have been the 90. Damn. So this is 90, this is 80, and so 90, because that's 100. So this is 90, this is 80, and that's 70. This one would have been 60. All right? So those are the 3 parallel lines right there, above. See, how did I do that wrong? 60, 50, 40, 30. I counted wrong. See, it starts there at 30. Yeah, I just didn't look right. Okay. Does that help you at all? I don't even know what that looks like out here. I don't know. I guess it's okay. I mean, some people can see a lot better in 3D than others. But you got the idea, right? Okay. Let's go on. All right, so the equation for the simple regression, okay, so why is this? Why is the exam slope smaller in the multiple? Now you know it's smaller because we took out that effect for exams. Because why? This is hard to, because there's a negative there's no negative correlations going on. Because there's a positive correlation between exams and homework and between homework and finals, and the effect of the homework is combined with exams. Yes, it's combined in the simple, so it inflates its slope. That looks good. because there's no correlation. No, that's wrong. This is it. All right, that's right here, sorry. Okay, so much words. You know, sometimes these are the hardest problems on exams. It's just read them carefully, especially because our next exam is all multiple choice. Well, all our exams are. So sometimes that makes it hard for people who just take your time and read it really carefully. Somebody once told me that on my exams, the multiple choice are really easy because they said, Ellen, you always write, the longest answer is always right, because I'm careful, and I would just not think about the other ones. And I realized that was true, and people were doing that, so I changed it. And often the longest answer is the wrong answer. I mean, I changed to make them all sound good. And I realized how much fun it is to write what I call those distractor wrong answers, and how easy it is to basically lie with words, make things sound good, you know? And I got to be such an expert at it that now people hate my melt. They say they're harder than the regular ones. But in a way, it's good because I think I'm really teaching something useful, because you pick up any newspaper or hear any argument, and people are always making it sound good. So that's probably the best skill you can learn, is to be able to detect it when it sounds good, that it's not, when it doesn't make sense. So I think it's hugely valuable, as important as learning statistics. It's just I never tried to write that way before. I said, boy, this is fun. Maybe I should be a writer. Because if you don't have to think about logic, you can just make things sound great. So anyway, so that's what I do. So don't think it's the longest. It's always the best. All right, now interactions. Okay. And then what are we going to do? Okay, we're almost done here. Interactions. Well, this is just going to be conceptual here. We're not going to try to figure out the slopes for the interactions, I'll tell you that. So, previously we saw how including an interaction term in multiple regression models with one or more binary predictor allowed for non-parallel slopes. With that, we could figure it out because binary predictors are so easy. They just have 0 or 1. Now we're going to do the same exact thing in the case of 2 or more quantitative predictors. So, on the last page, you may wonder how we knew those 3 lines would be parallel. In other words, how did we know that an improved homework score made just as much difference for students with high exam scores as for those with low? Really, we didn't. We didn't at all. But it's just a simple guess, but it's the guess that's at the heart of multiple regression. That's what multiple regression does. It makes that assumption. All right? It assumes that each predictor matters exactly the same amount, regardless of what values the other predictors have. So it assumes that the slope of each predictor is the same for all values of the other ones. So it makes predictions easy as long as the data fits it well enough. But often it doesn't fit. Often the effect of a predictor variable may change as the value of another predictor changes. For example, and I think it does, I thought of a likely example, I'm not sure, one that you can imagine. For example, I'm not sure if it's true or not, but this is what maybe not in this class, but in other classes it's sometimes true. For example, doing the homework may make more of a difference in raising final scores for those with low exam scores than for those with high exam scores. If that's the case, then there's an interaction between homework and exam scores, and we'd have to include a multiplicative term like we did before. That's an interaction term. Homework, the 2 x's are multiplied by each other, and you put a coefficient in front of it. And I tried to do a basic picture of this, and I hope it helps, but it might not. But so here, I'm trying to say, okay, now interactions, remember, how are you going to spot interactions between these? There's 4, okay, what is this? So this is the final. We're doing finals. The y-axis is finals. Now what else am I doing here? So this, I'm not drawing them in 3D. I'm putting the homework across here for each of them. Each one has the homework on this. And then I'm just, what am I doing here? I'm saying that people who have high exams, why did they do that? I said most of them have high up on top, so these little pictures are people with the high exams, and these are the people with the low exams down here. So these are people with high and low, high and low. I didn't draw it in 3D, I'm just showing it in 2D here. So these are the exams. And what's this? This is sort of the overall regression equation. So let's just, so what is interactions? Interactions, how are you going to spot them? This right here is that the groups, the two groups, so these are people with high and low. There's just two groups of people, high and low, high and low, high and low. The groups have what? The group slopes are not parallel. Non-parallel slopes. Okay? So let's pick out the interactions first. So there's an interaction, right? These have parallel slopes, the two groups. These have parallel slopes. These don't. So these two have interactions, okay? So this one has, that's where this comes from. This has an interaction and this does. These don't. So that's the easy part. Now let's remember confounding. What's confounding? Oh, so the confounder happens when? So if we're talking about causation, and we have these two prior groups, confounding. This means we're talking about these group A and group B, group A, you know, high, low, and they happen before. Excuse me. Do you realize how important this causation stuff is becoming? It's the hottest. I'm taking a break because my throat is. So I'm using this opportunity to tell you something that you probably might not know, is that this is the hottest new stuff everywhere. Every political science, everything, people are saying, hey, do you know anybody who talks about, I remember you teach all these confounders and causations. You know, that was your, it's been this way for 20 years for me. I've been very interested in that, and people didn't used to care about it so much. And now, because there's been some mathematical advances in that field, really very interesting stuff, it's the hottest new topic. So everybody says, hey, do you know anybody who can come and give a talk here who's really, you know, it's just become really important. And so it's good to, so it's, I feel very gratified or happy that this is, because I've always thought it's important. People want to know reasons why. They don't want to just make predictions, right? And now there's some innovative ways to do that with these, basically with causal pathways. And these, I can talk more about that later, but now my throat's better and I can teach again. So I know that you won't see it in other places, but you will. You are going to see it everywhere pretty soon, if you haven't already. And so I just want to try to get it right here. So when we're talking about causation, and you have these two prior groups, so what it would occur, confounding occurs when both conditions, both these conditions are met. Now, what are the two conditions? We looked at them before. When you're looking at these diagrams, we looked at them before. We said the first one is that you have to have different x averages for the two groups. So you have different x averages the two groups have different x averages. So that would be like this one. See, the average is here for homework and here. So it would be this one and this one have different x. These two have the same pretty much x average. And what's the other condition? That the overall slope, the overall slope, when you are looking at combining the two groups, the overall slope is not equal to the average of the two group slopes. So let's look at that. So the overall slope here is equal to it. Here it's equal, the overall would be equal to the average of these two. Do you see how the average of these two would be here? You know, they both have positive, they have the same slope. But this is not the same. And that's why it's confounding it. And here, too. So this is the overall slope. So these two also have confounding. These two have confounding. So I hope that helps. I know it's a little confusing. We're going to see this over and over again. But any questions on that? All right, let's see what else we have to do. So this is what we just talked about. And, wow, I thought I was only going to get this far. But now I went further. Okay. Let's see what we'll do here then. Do we want to move on? We might as well. Okay, so let's think about it then. All right, so assumptions. This is exactly the same as we had before, so you'll be relieved. Here, there's nothing new to learn. In order to make these inferences, now we're going to make inferences. Now that you understand, we're going to do some inferential statistics if you want. Do you still want to go on today? So we can, you look tired, I'm tired. I didn't think I was going to talk about this, but why not, you know? It's okay? What do you guys think? Because don't you want to get more of it in than I'll post the homework earlier, you'll have more time before the exam. I'm not going to make it due any earlier. I'll just compost it and you can start it. And if we don't do a good job, we can just cut this out. We'll see, you know. We'll just see how it goes because I didn't really think I was going to talk about this. But let's do it anyway. Okay? All right. All right, so chapter 36 is the assumptions before we can make these inferences. So what we've been doing so far is what have we been doing? We just describe the data we have. But now we want to make these inferences. And we want to, what we're going to do is we're going to do significance tests, just like we did before. In fact, we're going to do ANOVA again. We're going to do the F test, the chi-square test, and then on the individual slopes, the Z and the T. We're going to do, this is all review. We're going to do exactly the same formulas, the charts you did before with the sum of squares and all that. Same exact stuff you've already seen for groups when we compared groups with multiple groups. Now we're going to do it with these multiple slopes in multiple regression. Okay? So you've seen it all before. So the assumptions are the same as we had for simple linear regression, too. In order to make inferences about a larger population, we need to make some assumptions. And these are the same ones we made before, back in chapter what? I can't believe I wrote that. But it was back in chapter, I can't remember. Does that really say chapter question mark? It does. I have to edit that. But it was the same ones we had back. Here it is, right here. We've been doing it throughout. Here's for ANOVA when we did the F test. And when we did it for simple regression, we did it too. I mean, I just happened to turn to that. It's going to be exact. We even did all this for simple regression. You're going to see the same thing again. It's going to be so easy for you. And these are the same assumptions. Okay, so what are the assumptions? Remember what they were? That you have to, the data can be modeled as a random sample. Okay, so you need some, if you're going to make inferential statistics, it has to be built on some probability model that there was a random sample. We have to have some randomness there, right? So that's the first one. And that each of, so that's why I always say assume that this was, it's kind of cheating, assume it came from a random sample. We're going to talk more about that later, about how we can model it as a random sample and do other things besides just assuming it was. But that's to come. All right, so we assume that it's random sample. Now, we also assume that each of the predictor variables has a linear relation with the response variable. Now I know exactly where that came from, where we did this. So we look back, and we even drew little pictures, right, with way back here. There we go. Here are our assumptions. Back in chapter 27. Randomness. That it came from a random, that there's linearity. See, this looked good, Those look bad. So we already went through this. That we ran them. That there's a probability model. So that you check for linearity. And then what do? We want independence of the errors. So here we have independence. We don't want any clumping. Equal variation, equal variability. The error should be error fan shape is bad because there's way more spread up here than there is down here. And then what else? And that there's a normally distributed. That came in where? Normally distributed errors. Okay, so we did all this already. And to use the standard, each has a linear. To use the standard statistical tests and confidence intervals, we have to assume that the prediction errors, these random little errors, are independent, roughly normally distributed with equal variance. And you're often going to see this written as these errors, that's E for errors, are independent, identically distributed, normal, with an average of 0. They all average out to 0, right? We fit a model where they all average out to 0, and the same sigma that we estimate by our SD plus. Okay? All right. Now, these are the same assumptions. So let's check assumptions in the context of our example. So the 107 students were randomly chosen. They weren't, but pretend. It's really bad of me to do that, but they are very characteristic, but they were actually a separate group. But we're going to show you some techniques where we're going to do simulations where they are randomly chosen from a wider population and do different things to check this assumption later on. So for now, just assume they came from a large population. Now, the plots for homework versus final and exams versus final both showed a linear trend. We already saw that. And we can only check the third assumption, all this, after we do the analysis and plot the residuals. So we'll examine how to check this assumption after we do a significance test for the overall model. Okay? We'll be checking assumptions throughout in our courses. Most courses at higher level analysis, like 420, and if you go into the 400 level courses that are very applied, you do a huge amount of checking these assumptions. But what I love is getting around all that by just doing simulations, and re-randomization techniques, which is really cool. We're going to do after the exam. All right. Now, what should we do if the assumptions are violated? What should we do? Random sampling violated. This happens all the time, right? It does. Try to assess how closely your sample reflects the population. That's one thing. And also, plus other, we'll talk about later. For example, if your sample is all college students, you can't make inferences about adults, obviously. Linearity violated. If linearity is violated, we could try transforming the data, and that's to come, or try nonlinear functions. Errors not equal. Don't have equal variation, we can use data transformation or these non-parametric methods that are my favorite, and that's part 18. And errors not normal, again, you can use these re-randomization methods, the non-parametric methods, or data transfer. This is all stuff we're getting to. You'll see. But for now, let's just figure out how to do it. Okay. So, and you're not going to have, you're not going to be tested much on that because you don't understand. It's very hard to know when something looks, to check these assumptions until you see violations and you understand what to do with them and why. So I just want you to know them for now. We're not really going to be tested on them because it wouldn't help with understanding. You can't really understand what's good until you see what's bad and how to fix it, right? So you just understand it in a sort of, hopefully that pictorial way I showed you, and any questions I asked you on the exam would be super easy. Okay, now what are we going to do here? Okay, R squared. Testing how well our sample regression equation fits the population equation. Okay, so here's the idea. When we find these B's that give the best least squares fit for our particular sample, that's all we've done. Now, we have to check whether we'd expect them to be strong enough to accurately reflect what the true relation is in the population. See, we're just fitting something to one particular sample. And so we do these significance tests that tells us basically how likely we'd get this good a fit in our sample if in the population there's really nothing. And what's the probability of that? And that's what we're going to be doing. And that's the same type of significance test you always do. In your sample, yes, we got some kind of fit. But you know, think about it. Just by random chance, you can get some kind of fit. And so what we're doing is we're seeing the likelihood of getting that good a fit if there really was nothing. For example, let's say I randomly paired up. Check your homework average now and your exam, which got an exam, okay? You have a real correlation between those two. We should look at your data. We have a real correlation. But what if I just randomly just took all your homework scores and all your exam scores and just randomly paired them up? Just assigned to each one of you, gave you a random exam score. So you have your own homework and you get a random exam score. There's going to be some correlation between those two, even though there really isn't any reason to be, just by the luck of the draw. It's not going to be exactly zero, right? It could, by the luck of the draw, be pretty, you could get some correlation. So the question, and if you did it, the question is, just like when you flip a coin, it could be a fair coin, but you can flip it 10 times in a row and you can get all heads, right? So the question is, how likely is it? So we're going to actually do that. We're going to randomly pair up. This is what these significance tests do. With all these assumptions, they figure out that's when you figure out a p-value. That's what it means. How likely would it be to get that when the null is true, when nothing's going on? And that's what we're going to do here. And you have to make all these assumptions. But we're going to do it another way where we're actually going to, you'll see us randomly pair up all your scores and then see what you get. And that's another way. You know you'd expect zero, and that's another way to get a p-value. So it's nice that's called a re-randomization method. But that's at the heart of doing this, is that's why there has to be a random sample at the beginning. And then we make these assumptions about, if all these assumptions are true, we know a distribution. And we know it's going to be distributed, this multiple regression as a chi-squared or an F. So that's what's going to be that. We'll develop a test statistic, an F-stat, or a chi-square stat that's distributed a particular way we know, and we're going to do exactly the same thing here. So that's the basic idea. We've seen it over and over and over again. So here we go again. Let's just read it now. We found some fit for a particular sample, but before we go further, we have to check whether we should expect those slopes we came up to accurately reflect the betas we'd get for the whole population. Maybe they're just fitting some accidental features of our random sample. Maybe even our null, that all of them are equal to zero, would be as good within typical random jitter. So now that we have more than one slope, our first step is to test whether any of the slopes in the model are significant. So we're going to do the overall test, just like we did with the group means. If none of them are, there's not much point in exploring the model further. Okay? So we're going to test the overall regression effect with an F test, or a chi-square. So here is the overall regression effect here. And the null hypothesis is the usual. All the slopes, all the betas, are equal to zero in the population, right? And that's the same thing as R is equal to zero and R squared is equal to zero. or r squared is equal to 0. And it's the same thing as what? As our predicted y. We do just as good a job of predicting y by just taking the average y. So we have this model based on your homework and your exams. We might as well just take your average y, the average final, and predict. Everybody gets the average. I know it's different, but the homework and final and the exams aren't helping me at all. You know that's crazy for this model, but that's because we know homework and exams are really, but that's the mechanics of it. That's the idea. That's what it's going to tell us. And we're going to get a significant overall test. So that's it. Remember, all significance tests check how far some random sample landed from what was expected. We expect nothing, and it landed somewhere else. So with simple regression, we had the choice of using either a t-test or an f-test. Remember that? That was before break. Do you remember we could use t squared was the same as f? And if n was large enough, we could use either a z or a chi-squared. Remember, z squared was the same thing as chi-squared? Now, with multiple regression, we no longer have that choice. We have to use the f-test or the chi-square test. Why? Because, like before, with multiple groups, when we were comparing them, we can't boil down the difference between what we observe and what we expect on their null to a single number. The t and the z are single number, observed minus expected, right? We can't do that because with two or more slopes, we have to look at two or more differences. Some could be positive, others could be negative. So we can't just sum them up. What do? We have to square the differences before summing them up. So that gives you, what is that? That's like a measure of variance. So both the chi-square test and the f-test are based on comparing sum of squared differences, which are variances. So even though you really want to see if they're different, there's no way to, when you have multiple groups, that's just how you do it. And multiple slopes. So if the sample size is large enough, we can use the chi-square test. Otherwise, we use the f-test. So doesn't this almost sound like a broken record? Have you heard all this before? Doesn't it kind of sound like really like a broken record? It does to me. It sounds like so. So basically, what do I say here? So as n goes to infinity, I'll just write it this way because f goes to chi-squared. And as n goes to infinity, t goes to z. All right. Our infinity is 25. That's the cutoff we decided here. But I mean, this is the theory. Okay? I mean, when we say, all right, so let's turn the page. And let's just see. Oh, this is so easy. I could probably do it. This is exactly the same thing. We're just going to do exactly the same thing. Let's just do a quick chi-squared computation. Look, remember we already had chi-squared? R squared over 1 minus r squared times n. But now, so chi-squared is super easy. Let's just do this calculation. So what did they give us? This. Remember, chi-squared, we've done this before. Remember, is the chi-square test that we use for simple regression. It's our old friend. We can use it for multiple. All we have to do is change the degrees of freedom. This is exactly the same. So we can do it. We can say R. Why don't we just do that right now because I don't want to write all that out. Over 1 minus 0.62 squared. R squared over 1 minus r squared. There it is, like R. That's R. It's how much correlation we have. 1 minus how much error, basically. R squared over 1 minus r squared. That ratio is key. And then, just how big our sample size is. Bigger our sample size, more evidence we have. So we, what is n? 107. So this is times 107, right there. Okay, and I have that written down, 66.81. Wow, that's astronomical. That is huge. Remember the degrees of freedom for the chi-square test is in p minus 1, number of parameters in the model minus 1. All right, how many parameters in the model do we have? We have 1, that's 1 beta, 1, b, 2, 3. So our degrees of freedom is going to be p minus 1, which is 3 minus 1, which is 2. And we're just going to look down here, and we can get our critical values. This is so nice. Degrees of freedom is 2. And now it says, how big a chi-squared do we need to reject the null at 5%? There's 5%, 1%, and 0.1%. And here's, just look at this line. So here's for 5%. We need at least, that's our critical value. And look what we have, 66.81. Oh my gosh, definitely reject the null. And if we even if we want 1% significance, where's that? Do you see that? This is 9.21. And the last one is 13.82. So what do you conclude? Wow. We conclude tiny p. We've got a tiny p. We'd have a picture like, I'll just do the picture and then I'll quit. I got too excited because it's so easy to explain because we've already done all this before. So our picture would be like, that's 5.99. That's our, from here on in is 5%. And then we go 9.21. That's 1%. And then we have 0.1%. And where are we? 0.1% is that way. That one is, sorry, I don't want to rush. You have to leave. But we are off the charts. We are like, see what I mean? Our p-value, because what's our p? Our p is 66.81. 66.81 is going to be a tiny, tiny little, I'm sorry, I got carried away. We'll start here again tomorrow, next time. Thanks for your patience.